the Big Bang singularity. According to the Big Bang theory, the universe began from an incredibly hot, dense state.
I try not to think of what happened before Big Bang because I don't think there is an answer for it. There are certain theories. Some people think, our universe is recurring, so maybe there was another universe which collapsed and so on.
What happened before the Big Bang? Let's take a look at what science tells us. For more than 50 years, we have had clear scientific proof that our universe, as we know it, started from a hot, dense Big Bang. Or at least, we thought that was the story. The universe came into existence a finite amount of time ago, beginning with the Big Bang. Today, we know a lot more than we did back then, and the picture isn't quite as clear. Let's go back to the origin of space-time itself and try to understand this. 13.8 billion years ago, our universe started from a volume of space smaller than the size of a tennis ball. All matter and energy that we see today was concentrated in that small volume. With all this energy in a small space, the universe didn't collapse into a black hole. Instead, it started expanding exponentially and has been expanding ever since. The expansion of the universe was first observed by Vesto Slipher in the early 1920s, and in 1929, Edwin Hubble, who had access to some of the world's largest telescopes, gave the Hubble law. In the later years, scientists were able to build upon Hubble's work and observe distant galaxies and supernovae, and were shocked to learn the results. The universe wasn't just expanding, it was expanding at an accelerating rate. The universe, no matter how beautiful it is, contains a number of observable facts that demand an explanation. Some of these are the receding of the distant galaxies in proportion to their distance from us, which was first observed by Hubble himself. The universe at larger distances appears to be less clumpy and more uniform. The presence of an extremely cold but clearly visible background of black body radiation in all directions in space. One framework which is consistent with each and every one of these observations is the Big Bang. According to the Big Bang theory, our universe began 13.8 billion years ago in a very hot and dense, violent explosion of a very tiny primordial nugget. Over millions and millions of years, the universe cooled down, and it led to the formation of stars, galaxies, and planets. The universe is still expanding because of that explosion. This means that the universe was hotter and denser in the past. If we try to extrapolate far back into the history of our universe, things get exciting. In many respects, the Big Bang's central idea was that if you have a universe filled with matter and radiation that is expanding today, if you travel far enough back in time, you'll arrive at a state that is so hot and dense that the rules of physics itself break down. All that we can see in the universe today stretches 46 billion light years in all directions, and we can trace its origin back to a hot, dense, and rapidly expanding state. Intuitively, like many, you may be tempted to trace it back to a small, single hot, dense state, a singularity. But hold that temptation, as it is quite wrong. The Big Bang wasn't the beginning. That credit goes to inflation, and everyone should understand why. Before proceeding, be sure to leave a like for the algorithm and subscribe to our channel clicking the bell. This will encourage us to do better, and you'll never miss any of our weekly videos. Back to the story of our origins. Inflation is our best scientific theory as to what preceded the Big Bang. In 1979, a young physicist, Alan Guth, laid the foundation of the idea of the multiverse. He and his mate Henry Tye wanted to know how the particles might have been formed during the early universe. Alan discovered something exceptional about their equation, about how new particles were formed in the early universe. In the math of his equations, he found evidence that in the harsh environment of the early universe, gravity can be repulsive. The common notion of gravity that we humans have here on Earth is that gravity is attractive in nature, but the equations of the early universe were suggesting a different property to it. This repulsive gravity could drive apart everything around it and repel it, causing a massive expansion. This force was so powerful that it could take a molecule and blow it up to the size of a galaxy in less than a billionth of a blink of the eye. This spectacular realization gave birth to the theory of inflation. Instead of projecting the Big Bang all the way back to a singularity, inflation essentially states that there is a limit. You can return to a certain high temperature and density, but no further. This hot, dense, uniform condition, according to the grand notion of cosmic inflation, was preceded by a state where the universe did not contain matter and radiation, but rather a large amount of energy intrinsic to the fabric of space itself, which caused the universe to expand exponentially and at a constant, unchanging rate, causing the universe to be flat, empty, and uniform, up to the scale of quantum fluctuations, and then inflation ended, converting that intrinsic to space energy into matter and radiation. And this is where the hot Big Bang came from. The powerful gravity of inflation caused the bang in the Big Bang. This repulsive gravity caused the universe to expand outwards. Cosmic inflation not only solved the mystery that the Big Bang theory couldn't explain, but it also made several additional predictions that have subsequently been confirmed. There's still much we don't know about cosmic inflation, but research from the previous 3 decades strongly confirms the presence of an inflationary state that preceded and set up the hot Big Bang. Taken together, this is enough to tell us what the Big Bang is and isn't. It is the idea that in the distant past, our universe was hotter, denser, and more uniform. It's not the notion that things became arbitrarily hot and dense to the point that the rules of physics no longer apply. It is the idea that as the universe expanded, cooled, and gravitated, we destroyed our surplus antimatter, becoming protons, neutrons, light nuclei, atoms, and, eventually, stars, galaxies, and the universe we know today. It's no longer assumed that space and time arose from a singularity 13.8 billion years ago, and it is a collection of conditions that existed very early on, but was preceded by a distinct set of conditions: inflation. The Big Bang may not be the absolute beginnings of the universe, but it is the start of our universe as we know it. It's not the start, but it is our start. It may not be the full tale in and of itself, but it is an important element of the larger cosmic story that binds us all. A last question that might come to your minds is, what comes before this inflationary state? Well, we only have theoretical possibilities, with almost no data or information from that period in our universe to help us. It may have been eternal to the past, a real singularity before it, or something else. As far as our present observations go, we haven't even dreamed of a manner we could possibly know. Our laws of physics break at such extreme points of time. And talking about time, time itself was created after the Big Bang. It might be an emergent property of our universe, or it might have always been there. With our current understanding of the laws of physics, it's not possible to know more about the period before inflation. We'll keep looking for indications about the nature of inflation and what caused it. Keep all choices open as possibilities if you like. But remember that conjecture is no substitute for the finest that science has to give right now. But one thing is sure, inflation occurs prior to the Big Bang, and anyone who claims otherwise is more than 3 decades out of date. To Throughout the centuries, human beings have looked at the stars with astonishment, wonder, and curiosity, wondering what could be the origin of such magnificence and the nature of its evolution. These questions have been the subject of religious, philosophical, and scientific debate and disquisition since the earliest times of human history. All the greatest minds of the scientific world have asked themselves these questions, giving different answers and proposing theories sometimes conflicting with each other. Among these, one of the most famous, as well as the one currently accepted, is undoubtedly the Big Bang Theory. However, its fame is often accompanied by deep misunderstandings and false conceptions about its real meaning and scope, even by so-called experts in the field. For example, one of the most common errors about the Big Bang Theory is to believe that it is able to describe the origin of the universe. In fact, it represents an attempt to explain how it has evolved from a presumed initial event, characterized by conditions of density and temperature extremely high, but it's not able to explain how it really began the process of creation of the universe, or what actually could have existed before that event, or if, again, there can be something outside the universe as we know it today. Another gross misunderstanding is that, according to which the Big Bang is associated with some kind of giant explosion. The theory, in fact, proposes the purpose, unfortunately not fully achieved, as we shall see later, to describe the hypothesized expansion of the universe from a primordial state up to the size currently estimated on the basis of astronomical and astrophysical observations. Although most of the formulations of the theory describe an incredibly fast expansion of space, potentially greater than that of light, it's not possible to consider this process as an explosion in the usual sense of the term. Apart from this, it is always good to remember that, however magnificent, this physical mathematical construction is still a theory, perfectible, but also subject to possible refutations. Look, this is the cosmos. Each of these tiny lights represents an entire galaxy. Each is composed of hundreds of billions of stars. In shaping the universe, gravity builds a web-like structure of filaments that bind galaxies and galaxy clusters together along invisible bridges of gas and dark matter, hundreds of millions of light years long. Billions of galaxies form a web that permeates the entire universe and expands in all directions. And among all those galaxies, there's one in particular, spiral-shaped. Inside it, there is a bright star, a star like many others, around which 8 planets orbit, and one of them is inhabited by an animal species that only recently began to understand something of what surrounds it, making more discoveries in the last century than in its entire previous history. Only since a century ago, in fact, we humans know that everything that exists is formed by matter recycled from the stars, huge atomic furnaces that burn hydrogen and convert it into heavier and heavier elements, without which nothing we see could exist. But where do stars come from? Who created them? And here the eternal question arises. However, then something happened, and the singularity expanded with a tremendous emission of radiation. In an infinitesimal fraction of a second, the universe went from the size of an atom to the size of an orange. The universe began to exist, expanding and unfolding. It became larger and gradually began to cool. In just 100 seconds, it became as large as our solar system, with an extension of billions of kilometers. During this process, the massive energy began to cool and create matter in the form of billions of subatomic particles, the first nuclei of existence itself. About half of these particles were composed of matter, the same substance of which we are made and everything around us. The other half was formed by the opposite of matter, a substance called antimatter. And when matter and antimatter meet, they destroy each other, in a process called annihilation. The birth of the universe has therefore involved a huge loss of matter and energy. Fortunately, the amount of matter was slightly greater than the amount of antimatter, so the matter survived, even if only thanks to a particle in a billion. And it was up to this infinitesimal residue to give origin to the universe we know today.